Hey, I'm Charlie Thompson, and this is a video about latitude, noon sun angle, and trees. So I've said before a couple times, I'll just keep saying it until the sun goes dark, that latitude is the reason for 95% of everything that happens in physical geography, or rather, latitude influences. Latitude has an effect on. Latitude is the reason that that pattern exists. So latitude is the most important factor in physical geography. So in this diagram, the subsolar point is the equator. If you are at the subsolar point, the angle of the sun to the horizon would be 90 degrees. The sun would be directly overhead if you were at the equator. We're using the formula of the noon sun angle equals 90 degrees minus the zenith angle, and the zenith angle is the angle between you and the subsolar point. So if you're at the subsolar point, your noon sun angle is 90 degrees. For every degree you get away from the subsolar point, the noon sun angle gets away from 90 degrees by 1 degree. So if you were at 10 degrees north, 90 minus 10 is 80, so the sun would be hitting the surface at an 80 degree angle. 70 degree, 60, 50, at 45 degrees on this day, and it's got to be one of the equinoxes because the sun is, or rather the subsolar point's over the equator. If we were at 45 degrees north, the sun would be hitting the surface at a 45 degree angle, 50 degree angle, 60 degree angle, 70, 80, and finally, the sun's beams would just be parallel to the surface of the Earth at the North Pole. So far this is all just review. This is stuff that you should be aware of, and if not, great. And I thought, what would be a fun assignment would be to give students set up the problem of, your latitude and you need to use photovoltaic panels to make electricity from energy from the sun. So if you know what your latitude is, you should be able to figure out what the angle of the solar panels to the ground is as a function of your latitude. And it turns out that the angle of the panels to the ground should just be equal to whatever your latitude is. For example, if you were at the equator again, the subsolar point's the equator for this whole video, I'm just going to pretend that it's the equinox on every single day. So if you're at the equator, you would want your solar panels to be flat on the ground because the sun would be directly overhead, shining down on them at a 90 degree angle. If you were at 45 degrees north, you would want your solar panels, and this is a 45 degree angle, you would want your solar panels mounted at a 45 degree angle to the ground. And finally, if you're at the North Pole, you would want your solar panels to be at a 90 degree angle to the horizon, to the ground, because the angle of the rays from the sun are also, they're parallel to the ground, right? So you'd want the solar panels to be perpendicular, 90 degrees away from that. So if the rays from the sun are coming in parallel to the ground, then because your latitude is 90 degrees, then the angle of your solar panels to the ground should be 90 degrees. So I thought it was a great idea. It's totally applicable. Like where I live, the angle of my roof was designed to take advantage of solar panels for maximum effect. It means that my roof is a little steeper than most. Well, the angle of my roof should be about 40 degrees because that's the angle. Well, our latitude is 40 degrees north. So on the equinoxes, the sun would be hitting the ground at a 60 degree angle. Anyway, the angle for the photovoltaic, the problem with the whole thing, trying to make this into an assignment question, is that I think by the time you explain it so that people understand it, there's nothing left to do, right? I mean, once you understand, whatever your latitude is, that's the angle that your solar panel should be to the ground. Once you understand that, as long as you know your latitude, you know what the angle of the solar panel is. There's like no work to do. There's no thought. It's just, if my latitude is 0, the angle of the solar panel to the ground would be 0. If I'm at the North Pole, where my latitude is 90, then the angle of the solar panel to the ground is 90. But, it occurred to me that this has effects outside of solar panels. So here's the noon sun angle. on the December solstice. Here's the noon sun angle if you're at the equator on the June solstice. So the angle of the sun goes back and forth, changes by about 47 degrees over the course of a year. But I realized that if you look at the world this way, that's not really accurate, right? I mean, there's nobody... Hang on. Let me show you a picture. That'll explain things. So noon sun angles at the solstices at the equator. Noon sun angles at 40 degrees north. So there's still a difference. This is the winter sun. This is the summer sun. So there's still a difference of about 47 degrees between summer and winter. But you can see that instead of the angles being 66.5 degrees above the horizon, 66.5 degrees above the horizon. So it's going to be 66.5, 90 degrees, back down to 66, up to 90, back down to 66. At 40 degrees north, it's going to go from, I think it's like 26 to 73 and back and forth. So the angle is changing by 47 degrees regardless of where you are, but those angles are different. 26 degree angle in the winter, 73 degree angle in the summer if you are at 40 degrees north. If you're at 60 degrees north, I'm not going to try to do the math off the top of my head, but throughout the year, all of the angles are going to be, well, if we compare 40 degrees and 60 degrees, the angle of the sun is going to be 20 degrees lower because our latitude is 20 degrees higher. So, well, that makes this easy. So instead of 26 degrees in the wintertime, the angle at 60 degrees north would be 6 degrees. So the sun would be 6 degrees above the horizon instead of 26 degrees where we are. So that's the way it would look if you're hovering in space, but really the way it would look is like that. Because if you're standing at the equator, you'd be standing with your feet on the ground and your head above the ground. So this is more accurate to the way the noon sun angle would look if you're at the equator. The sun goes from, 66.5 degrees to 90, back to 66, back to 90 to 66.5 over the course of a year. At 40 degrees, so that's the way the diagram looks, but then if you rotate the Earth so that it looks the way it would look to us, you can see that the angle is going from 26 to 73, back to 26 at 40 degrees. And at 60 degrees, the angle of the sun is going from 6 degrees above the horizon to 53 degrees above the horizon. So it occurred to me, this isn't just important for solar panels, it's very important for the angle of the sun. The closer to vertical, the more powerful the rays of the sun are, the more energy that they transfer. And the energy from the sun, a lot of it's absorbed by plants. So if you're a plant, you're getting fed by the sun. That's where your energy comes from. You're taking photons and you're converting oxygen and water into sugars and producing oxygen as a waste product. And it occurred to me that trees in the tropics look different than trees at high latitude. So here we've got a low latitude tree in the tropics. It's some sort of acacia tree. And it occurred to me, because I was thinking about tropical trees, that they're very flat. And here is a shot of palm trees with the sun directly overhead. So it could be at the equator on the equinox. It could be the Tropic of Cancer on the June solstice. Could be the Tropic of Capricorn on the December solstice. But in any event, you can tell from the shadows that the sun is directly over these palms. Here we've got a high latitude tree, something in a pine, maybe a hemlock, but instead of being flat, it's much more vertical. And I thought, there's a relationship between the shape of trees and their latitude. So if you're in the tropics, so I've put this is then the tropical acacia tree, showing the noon sun angles for the June solstice and the December solstice. So they're pretty much always directly overhead. So if you're a tree, you'd want to be a big flat tree. And I thought, oh, that looks just like the right angle for a solar panel. 0 degrees to the horizon. In the mid-latitudes where we live, I thought, they're not flat, they're not vertical, they're kind of in between because the angle of the sun is going from 73 degrees down to 26 degrees. And so this is a silhouette of a valley oak tree. And I thought, oh yeah, you can really see that the shape of this tree is really well adapted, really well evolved for that latitude. And then finally, last but not least, I realized, oh, pine trees, all the conifers, all the pine trees, they have a more vertical growth form, which totally makes sense. If the sun is coming in like at 60 degrees north in the winter, the sun's coming in at a 6-degree angle. In the summertime, the best you can do at 60 degrees north is the sun is about 53 degrees above the horizon. So that's it. That's your quick explainer of the relationship between tree shape and latitude and the optimal angle of solar panels. All of these, I think, are great ways of emphasizing the importance of latitude in physical geography. Often in ways, and hopefully in a way that you hadn't thought of, in a way that you hadn't realized, in a way that hopefully you'll now be aware of going forward. That's it for this video. I hope you enjoyed the tree video.